Okay. Good morning, everyone, and welcome to a new session of the Netpore webinar. For this month, we have a Dr. Alexander Tesler. He will be our only speaker today. And Dr. Tesler is currently a postdoctoral fellow at the Friedrich Alexander University in Erlangen-Nuremberg. And he receives his Master of Science in Chemical Engineering from Technion and his PhD in chemistry in the Department of Materials and Interfaces from Weizmann Institute of Science. And after graduating from his PhD, he traveled to different universities, including Harvard University, studying mechanically durable omniphobic slippery surfaces. And his scientific interests range from the omniphobic surfaces to self-assembly of monolayers, plasmonic materials, and membrane technologies. And in today's talk, Alexander will discuss non-wettable ultra-slippery surfaces. So please, Alexander, the floor is yours.
Thank you very much. Welcome to this webinar. My name is again Alexander Tesler, and I'm from Friedrich Alexander University at Erlangen. And what I want to talk today is about non-wettable ultra-slippery, what we call aerophilic surfaces. And I want to start from this top 10 humanity problems as discussed by Richard Smalley, Nobel laureate in 2003. And as you see, the first one is energy and the second one is water. So energy is actually crucial for the rest. But again, without water, we cannot live. So water equal to life. Most of the Earth's surface is covered by water. It's about 71%. Only 3.5% of it is fresh. Most of it, about 70%, is located in the ice and glaciers, and only 30% in groundwater. So again, water is life, but about billion people lack access to improved water resources. 80% of diseases in developed countries are water related. And also, as was predicted a few years ago, half of the world's population will suffer from a water stress. You see here map of water-related conflicts in the last 4,500 years. And you see it was quite a lot of conflicts during this time. If we speak about Europe, even now, water stress affects 20% of a European territory and 30% of European population annually. Countries like Southern Europe suffer from droughts, which causes enormous, actually, damage and expenses. So, in addition to problems that we have with water, we have another problem known as chemical or biological fouling. So what is chemical or biological fouling? Is just a accumulation of unwanted materials on surface which deteriorate our functionality of the devices, materials, surfaces, and so on. Here you can see several examples like fog, ice, crushing of concrete through freeze-thaw resistance or cycles, corrosion and sedimentation in pipes, fungi fouling, almost everyone has it in its apartment, on the walls every winter, biofouling of membranes for desalination of water and on ship hulls, and finally bacterial fouling on medical devices like catheters and implants. If we think only about shipping industry, it was shown actually 10 years ago that amount of pollution just from shipping industry is huge in terms of carbon dioxide, sulfur dioxide, NOxes, and particle matter. So if we take data from 2007 to 2012, about 1 gigaton of carbon dioxide was polluted annually, which is about 3.5 annual global carbon dioxide emissions. And this number is just growing all the time. On the other hand, ocean, seas are in constant movement. And since they are in constant movement, they can be used as wonderful renewable energy source. As again was calculated, the beach area of the United States can cover most of its requirements for the energy. However, there are fouling problems that actually prevent, in many cases, to use such large amount of energy in real applications. From that point of view, superhydrophobic surfaces can actually reduce the contact between solid surfaces and surrounding liquids. However, they suffer from several problems. And this will be my talk for today. First of all, I briefly introduce you in superhydrophobic or aerophilic surfaces. I wrote how to make these surfaces ultra slippery, and I will show you several applications for what we have, and then summarize this talk. So, just brief reminder about wetting of surfaces. It was about more than 200 years ago when Young actually displayed relation between three different interfacial energies like solid vapor, liquid vapor, and solid liquid, and derive this equation, which is actually known as Young equation, for smooth, atomically smooth, chemically homogeneous surfaces. Now, this is actually pure theoretical value because we don't know how to produce such surfaces with such a homogeneity or chemical homogeneity. So, in almost 150 years later, Wenzel introduced more realistic value of roughness to this equation, which is R, and displayed it for state when droplet stay round on the surface, yet the droplet experience or follow the morphology of a solid state, and this is why it pinned to the surface. So this state, also called pinning state or homogeneous state, it's known as Wenzel state, and the only difference is by introduction of this roughness parameter. 10 years later, Casey and Baxter introduced additional correction to this model when they introduced the surface fraction coefficient, which displays how much of the surface actually is real in touch with a solid substrate. And of course, the most famous example of these surfaces is lotus leaf. So here, droplet experience a heterogeneous wetting when it is partially in contact with solid state and then partially is still in contact with air. So we work on titanium as a structural materials. Why titanium? Because titanium is a high melting point and a low specific gravity material, so it's very light, but it has good corrosion resistance and high strength. And also it is biocompatible, so it's used as a main material in almost all implants that we can put into the human body. So all these applications actually use quite a lot of titanium, among which this is a Airbus using now tons of titanium to build their aircraft. So this is why it is interesting material. Since we are an electrochemical laboratory, so approach was to use a relatively simple approach to make it rough, to make surface rough, without any lithography or complex processes. Now, when we talk about electrochemistry, it's very simple cell. It consists just of two electrodes. Titanium is an anode, steel is a cathode, and the basic electrolyte in between. Eh, and then after formation of rough surface, we just functionalize it with fluorophosphate ester molecule, like you see here. So in general, modification of bare titanium into aerophilic titanium is very, very cheap. So how do we know that we produce rough surface and not dense surface? We follow simply by current density measurements, and we see that with time it is increasing. So it means that more and more metallic surface is exposed to the electrochemical reaction. In the case of dense non-porous film, it will stay more or less similar to the initial. Some surface characterizations of our surfaces. So here you see SEM images of bare titanium alloy. So this is grade 5 alpha beta alloy, and this is typical micrographs of such alloy with alpha and beta phases. After anodization, we have this kind of surface. So it is rough. It's a hierarchically rough with micro scale protrusions and which are by itself nanoscaled. After functionalization, we have more or less the same morphology. XPS clearly shows formation of a self-assembly monolayer of fluorinated surfactant on the surface, for example, with sheaths of carbon to the formation of CF2, CF3 bonds, appearance of fluorine, phosphorus, and reduction in the signals of titanium and oxygen. Here are cross-sectional images of the surface. So here is SEM, TEM images. And from XRD, what we see that this alumina, a rough alumina layer is actually amorphous because we do not see appearance of any crystalline phases of alumina like anatase or rutile, and we only see phases of alpha and beta from a bare titanium alloy. Now, after functionalization, we had a problem. So here, top movie, you see that water does not stick to the surface. And then we cannot measure standard goniometric measurements such as contact angle, which is a minimal in this case. So if a droplet does not touch the surface, we try to land it on the surface, it just rolled out very quickly. So what we can do, we can measure contact angle hysteresis like here, which is quite negligible in this case. And then we need to use another techniques how to characterize the surface. Now, in collaboration with Professor Ras from Alta University, we did what's called micropipette force sensor. So this sensor actually measures friction force, direct friction force on the surface, and the droplet is actually sitting on the capillary. From these measurements and also from oscillating drop tribology, which is another technique to measure friction force, we can derive this plot, which actually characterize state-of-the-art superhydrophobic surfaces, which are development in recent years. And among all engineeringly available systems, our surfaces are the most slippery one. So there is one more slippery system, which is etched silicon or dark silicon, black silicon. But engineeringly, it is not relevant because it's not mechanically stable. On the other hand, our system is mechanically stable. So here you see several movies. Here it is water jet of 70 psi, which is equivalent to impinging mass of 900 grams, almost 1 kilogram, and surface surviving it easily. Here you see bending, twisting of these surfaces underwater, and they still reflective, meaning that they preserve their stability, wetting stability, even when it's bended significantly or twisted or whatever. It also survive beads of tens of thousands heavy particles like here, and the contact angle hysteresis after this experiment was still lower than 10 degree. So here you can see hysteresis before the experiment and here after the experiment. So we still experienced low adhesion from one side, and the hysteresis again was well below 10 degrees. And so far so good, everything is nice, but now we will go, or I want to introduce you several concepts that were actually um, shown in the literature. And one of them is, what about stability of this layer of air when you put your samples underwater? And this is paper in Physical Review Letter from Ulrich Steiner group at Cambridge, where he says that underwater superhydrophobicity is metastable. What does it mean? It means that if it is metastable, it's susceptible to any small perturbation in any condition, for example, pressure, temperature, and so on, or vibrations. It means that you cannot predict exact longevity of this protective air layer on the surface. And indeed, he did some model and found that his surfaces can survive at 50 centimeters depth for 44 hours. This is why another research from Ivan Parkin group at the University College of London demonstrated that anti-biofouling properties of such superhydrophobic sources are short-lived. Why they are short-lived? Because they actually lose this air protective layer within very short time, exposing high surface area surfaces for attachment of bacteria. For example, now you have more surface area, bacteria will attach more easily. And in all the cases, they speak about metastability of this air trapped on the surface. At the same time, about 20 years ago, Abraham Marmur from Technion theoretically predicted that underwater superhydrophobicity can be feasible. But to say if your system is stable or metastable, we need actually to make much more experiments rather than just simple goniometry, because not contact angle hysteresis will give us this data. For understanding if developed superhydrophobic surface is in stable or in a metastable state, we need to know several parameters. One of them is roughness or roughness factor. So this is dimensionless roughness as described by Wenzel. Solid liquid area fraction, or how much of our solid surface actually in touch with surrounding liquid, and also Young contact angle, which is in general non-measurable value. And then we need to do some measurements and then some assumptions. First, assumption is how to measure Young contact angle. And here we can use what's called the most stable contact angle, which is value measured on as flat or as smooth as possible surface of the same hydrophobic origin. So if we use a hydrophobic molecule, the surface should be flat and smooth as much as possible with the same molecule on the surface. So here we polished our samples to mirror-like finish. You can see it here. And even after that, we cannot measure one single value, meaning that we don't know how to measure this most stable contact angle. But what we know that it will be within the limiting cases. What are limiting cases? These are advancing and receding contact angle. So advancing angle is when we infuse more and more liquid, and receding when we actually withdraw this liquid. So advancing is the higher contact angle, apparent contact angle, and receding is the lowest apparent contact angle. And young contact angle and the most stable contact angle will be somewhere within this range. Roughness parameter we can get by several techniques such as AFM, atomic force microscopy, optical profilometry, or laser confocal microscopy. In this case, we use AFM, and we got some roughness parameter. And solid liquid area fraction, we know how to measure it with just simple reflectance microscopy. Here is the image of superhydrophobic surface underwater, and this flat area are a plastron, and dark spots are actually the pinning points, or where the water actually touches solid surface. And it was confirmed by confocal microscopy here. So we have here water, air, and solid surface. And then we can use two thermodynamic theories, one suggested by Lafuma and Curie in 2003, and one suggested by Marmor in 2006. So if we use Lafuma and Curie, what we can do, we can calculate the critical contact angle from all these measurements, which means that if our surfaces are above this critical contact angle, so in this area, the surface will be in stable Casey-Baxter state. If they are below this area, it means that the surface can be or in metastable Casey-Baxter or in stable Wenzel state, one of them. So here we see that with all measurements that we did, it may suggest that our surfaces may be, I do not say they are, but may be in stable area. And the same one we have with Marmor model, where we have this line is a solid liquid area fraction as we calculated from such images. And here is advancing, and here is receding contact angles on flat actually surfaces. And also here, so if we are above this line, above this solid liquid area fraction line, we are in stable plastron. If we are below it, it is just metastable plastron. And also here, the model suggests that we may be, so these surfaces may be in stable plastron conditions. So let's see. First of all, this is one of the experiments that we did. And what you see here is just piece of metal float on water surface. Now, this is piece of titanium, relatively heavy, without a superhydrophobic surface. It just will sink immediately to the bottom. This sample was floating for 133 days. And here you see meniscus. So this is front side, and you see this meniscus formed. And here you see the back side with this huge air bubble on the surface of this titanium metal piece. And this is actually what allow us, or this piece, to float on water. This plastron layer, this air trapped on the surface. Again, let's see how it behaves at 50 centimeters L, as Ulrich Steiner showed, for 44 hours. So this sample was 2 weeks at 50 centimeters of water, and when it was removed, it was completely dry. It is still reflective underwater. You can see it here and here, and we do not see any differences in sliding angles or pinning of the droplets on the surface. So it survives at least 336 hours at the same 50 centimeters of water. After 67 days or 1600 hours, we do see that partial degradation of surface. About 10% of area was already wetted by water, and you can see it here by bright gray color. But again, the rest was had very little adhesion to water, and also in some cases we see that hysteresis is higher, and in some areas is still low. Again, if we compare it to Ulrich Steiner data, it is more than, it's about 40 times longer time that it was previously shown. Now, we did compilation of almost all literature about underwater application of superhydrophobic surfaces, and we have here different results at different depth. Several of them only measured it at 50 centimeters. All of them failed within several hours, while our surface was much stable. Now, we compete here actually with this kind of bug, which is live organism, and it showed very long plastron stability also. And so it means that indeed the plastron stability and existence underwater is feasible. But how to actually define stability? Here are several examples of superhydrophobic surfaces underwater with plastron lifetime, and it was shown or actually described that if your plastron is 30 days long, it is ultra stable. If it is 50 days long, it has defined as infinite plastron lifetime. So currently we have 4 times longer plastron stability than infinite plastron lifetime. So we have it up to 2 and 8 days immersed continuously underwater, and when it's taken out, they are dry. But next question is if it repels only water. And the answer is no. Here you see example of blood. This is fresh pig's blood, and this is blood on superhydrophilic or as anodized titanium surface. Now, this is how it looks like under optical microscope, the morphology of bare titanium, and this is of blood, and this is a contact angle of blood on this superhydrophilic surface. So contact angle is about 1-2 degrees only, so it wets almost completely the area. When functionalized with fluorinated surfactant, the contact angle changes to 170 degrees or even higher. So this is 10 microliters droplet of blood, which is relatively heavy. But if we see on this satellite, which is a small droplet, it is almost round, meaning that actual contact angle is about 180 or reaching 180 degrees. So again, we had a problem how to land it and stop it on the surface. So you see here that adhesion of blood to the surface is very low. Hysteresis is very low. And actually blood can be removed easily by paper tissue, leaving behind completely free, blood-free surface. What about longevity? So this sample was immersed once. This sample was immersed 100 times for 1 second each. And what we see here, there is no difference between exposed here and unexposed area. So at least 100 times of immersion, it survives. Later on, we did the sequential experiments of immersion for different periods of time. And up to 1 hour, we did not see any attachment of blood to the surface. After 2 hours, we do see some small spots on the edges mainly, which were removed simply by rinse it in water. So, and here you can see again this reflectivity of the surface, which is due to the total internal reflectance in the thin air layer. Next was biofouling. So bacteria is actually swim in aqueous media. And then we use the sliding window like here to measure kinetics of binding for several actually hours, what we show here up to 150 minutes. And here is the kinetic results, which means that if we have bare or rough surface, there is no significant difference in between. But if it is super hydrophilic or hydrophobic or aerophilic surface, the plastron actually prevents bacteria from touching the surface and then settle on it. So after washing these samples, after about 4 hours, we can measure the amount of firmly attached bacteria. And here we see significant difference between both bare and superhydrophilic, while actually superhydrophilic behaves even worse than the bare one, indicating that a lot of surface area that it provides indeed make these samples susceptible even better to bacterial attachment. Next was to show how it behaves against marine organism, and in this case we used macrofoulers such as mussels and barnacles. Now, mussels are known that they secrete a bioglue like dopamine and attach firmly to the surface. On the other hand, barnacles known to secrete biocement, which again help them to glue to the surface, and it is not easy to remove them from the surface. In all the cases, so in case of mussels, this was the first time when superhydrophobic surface can completely prevent adhesion of mussels to the surface. So no one of mussels that was put on the surface was attached. Again, this is because they should sense solid state, while air plastron can actually disturb this sensing of touching this surface. On the other hand, barnacles do attach, but the strength of adhesion was much lower than on bare, control, and hydrophilic surface, and was smaller or of the same order of magnitude as state-of-the-art anti-biofouling paint. Now, if we take in consideration the price per meter square, paint cost hundreds of euros. Our treatment cost, I believe, less than $1 or €1. Now I want to summarize this talk. So first of all, long-term trapping of air plastron is feasible underwater. So we can show it already that at least 4 times infinite plastron can keep its properties. Now, from the other side, conventional goniometric measurements like contact angle and contact angle hysteresis do not provide any information, meaningful information on these surfaces, simply because in some cases we cannot measure it, and in some cases they do not explicitly tell us if wetting regime is stable or metastable. This is why we urgently need advanced characterization techniques to obtain all required information to make explicit understanding of if our surface is in stable, or our plastron actually is stable or metastable state. And what are these parameters? First of all, it is roughness, it is plastron shape, its solid liquid area fraction, and most stable contact angle. With that, we can measure or actually calculate the critical contact angle, which can tell us explicitly about stability of air trapped underwater. Why? Because all wetting related phenomena, such as corrosion and biofouling, actually decay with stability of this air plastron on the surface, because it's actually eliminate a physical touch between corrosive liquid and solid surface. Now I want to acknowledge all people that were contribute to this work. From FAU, from Friedrich Alexander University, we are actually three groups: biophysics group, a group of surface science and corrosion, and University Clinicum, Aalto University in Finland, leading by Robin Rass, Harvard University, and NDSU, North Dakota State University, did the marine anti-biofouling experiments, and also Avi Marmur from Technion, which we have fruitful discussions about this topic. And of course, funding from Friedrich Alexander University, German Science Foundation, and also fellowship from Emerging Talent Initiative. And here I want to show you some funny stuff you can do with such surfaces. When this ruler has electrostatic electricity and droplets, you can actually direct movement of droplet in specific direction, or even to remove it just by electrostatic electricity, while droplet jump on the surface and then jump back to the ruler. Thank you very much for listening, and if you have any questions, I will be happy to answer it.
Thank you very much, Alexander, for your very interesting talk. Are there any questions from the audience? Oh, there is one.
Yep.
Please.
Thank you very much, Alexander. I was working on photovoltaic solar panels, glasses, which is tempered glass, which is used at the very top of the panel to protect the actual material against corrosion or falling. Actually, it has good applications in this. I was listening to your progress. It's very much applicable to be applied on tempered glass, which is used in encapsulation of photovoltaics.
Mm-hmm.
Because it often happens that we have biofouling or corrosion on the glass, and so I think this technique will be really a good idea to apply.
Yeah, so first of all, when we talk about photovoltaics, we think about, first of all, about coating the surface itself. For example, if you have a contamination even from the dust, so sand, whatever, then these surfaces actually have a self-cleaning property. So you just need to put a little bit water, and then it will remove completely. So once you have a rain, it will renew the this panels, and then you will have full efficiency as it is supposed to be. This is from one side. In this case, we need a transparent system.
Yeah.
Yeah, so just to allow full
Transmission of light. Yeah.
exactly, so full light spectrum to propagate in. So yeah, so this is one of the applications that we work on. But again, you are right. So also corrosion and also biofouling of such surfaces are of great interest, because again, with time it will degrade, and relatively simple
Right. Right.
approach how to protect it can actually improve longevity of all these systems. I completely agree, and
Yeah.
these are of course of great interest also for us. So because in general our laboratory also work on uh, photocatalytic materials. So, and of
Uh,
course, yeah,
just a quick question: do you also do corrosion testing on glass as well? Because we have few samples we are looking for corrosion testing. The companies charge us a lot. Would that be
we,
possible to?
yeah, we do mainly on metals. So we do corrosion test for sure, but we do it mainly on metals currently.
Okay.
Of course, we can do it on other metal or other surfaces too. Um, so yeah, so we have a already. So this is just one part of my research. The second, of course, is corrosion resistance, and we have pretty nice results on corrosion resistance of these surfaces, not
Right.
just in a like pure water, but also in contaminated water with high concentration of ions. Yeah, and this is why, because we want to work, so we want to take this technology. The problem of this technology is that so far everything was shown metastable. This is mostly the first time that we can actually identify simple technique for stable system, and then we should take it underwater. Now, underwater means most of it is salt water, salty water, a lot of
Okay. So
chloride
ions
ions.
have a role. Yeah.
So, and
Right.
then we need to keep the protection also in this such of environment, and we have this data already. Yes,
Do you also use titanium materials included in there, or because we are already
we
working
have
with?
different metals. Titanium was just one of them. Yeah,
Okay.
yeah,
Perfect.
yeah.
Thank you so much. Very interesting.
Thank you.
Thank you. So we have a raised hand and then a question from Idalina, which is written in the message. But I will ask Oran Sisman if he has a question.
Thank you very much for the presentation, Alexander. And I have one question. As we know, water is a Newtonian liquid. Have you tried the viscoelastic liquid? How these theory and these calculations are changing, or how the behavior is changing when the elastic property of liquid emerged?
Yeah. So first of all, we have blood. Blood is a non-Newtonian liquid, and it still works. Um, this is a good question. We did not so because water-related phenomena are mainly interest of us. We use mainly with water-based liquids. A good question how it will behave on viscous um, liquids. I believe if these liquids up to some surface tension, it will behave normally, and it will decay with after some level of surface tension of these liquids, I believe. These are also oil philic surface, right? So they actually like or air or oil. So everything which is water based will be repelled. Everything which is oil based probably will be not or up to some extent. All the rest, it is good question. I cannot tell you now, but of course we can test it. So and again, the issue of these samples that everyone can make it at home. So you don't need any special equipment. You take simple power supply that you can buy everywhere. Two pieces of metal, one of them is titanium, one of them can be everything. Cathode can be almost everything. You put it in a aqueous electrolyte of sodium hydroxide, and that's it. You apply for 30 minutes and you're ready, more or less. And then you just need to modify it with, again, wet chemistry of surfactant, and you're ready. So you don't need any special equipment. You don't need any special, actually, knowledge to make it. Everyone can do it at home, truly speaking. So, and this is why it is beautiful, because in addition to that, electrochemistry in general is highly reproducible technique, and even in laboratory conditions, we can make samples of 20 by 20 centimeters, which are very big in general. But okay, this is one. We work on also another types of surfaces or surface roughness made by another techniques, which we also think will fit. And here we can actually adjust specific parameters, and maybe then to improve even this plastron stability, and then probably it will also go to lower standard liquids, non-Newtonian liquids, and so on. Yeah. So.
Okay, thank you.
Thank you. So we have one last question from Idalina. She asks, did you ever try to coat plastic surfaces?
We tried to coat plastic surfaces, but with this specific molecule, we need oxides. So, or oxide or hydroxide units on the surface. So in general, almost any surface is oxidized. However, metals, glasses, ceramics have more hydroxyl units. And this is why we generally work with such materials. With polymers, we need to fit a polymer with specific units to be able to make the self-assembly monolayer on polymer surface. This is from if we use this specific molecule. If we do not use this specific molecule and we use another molecules which based on another chemistry, then we can do it also there. But in this case, we should produce also similar roughness on that specific polymer, which I believe it's not so easy. So currently we do not use polymers in our research, but mainly metals, metal oxides, ceramics, glasses, and so on.
Okay. Thank you, Alexander, for your very nice presentation and lots of interesting insights on these materials and techniques. So, and thank you to the audience
Thank
for
you very much.
very interesting questions.
Thank you.
We will meet again in December for another webinar from the Netpore project. So please check on the website for the program. And thank you everyone for attending. Have a nice day.
Bye.